is the last question I'm going to do from chapter 2. And in this case, they give us another one of these polynomial subspaces. We're not asked to prove it's a subspace. You might like to make sure, mentally check that it is. It is in fact a subspace of P2, and it has the following properties. These are all the polynomials of degree at most 2, which are 0 at 2 and minus 1. Again, several ways of doing this. You could, in fact, because you know they're polynomials only of degree 2 and you know 2 of the roots of them, you can sort of write down the family of quadratics that satisfy this particular condition and do it that way. But we may have a more complicated problem, for example, where I've got a larger set and it's not so easy to write everything down. So I'm going to do it in a slightly more general way, which I hope will give you some ideas you can use in other similar kinds of problems. So if it's a subspace, then it's a vector space in its own right, so it must have a basis. And if it's got a basis, then it must have a dimension. So the way I'm going to do this is I'm going to write down my general object in P2, and that's just going to be a polynomial of degree at most 2. So there it is, ax squared plus bx plus c. Now I'm going to use the fact that I know what p of 2 and p of minus 1 is. So if I plug in 2, I get 4a plus 2b plus c, and that's got to be 0. And if I plug in minus 1, I get a minus b plus c, and that's got to be 0. And so I end up with these two equations. Now what on earth do I do with the two equations? Well, one thing that would be nice to do is I've got two equations with 3 unknowns in them. I can get rid of one of the 2 unknowns, well, one of the 3 unknowns. So the easiest one, you can get rid of any one you like, it doesn't matter, but the easiest one to get rid of is probably C in this case. So I might just subtract these. I'll take equation 1 minus equation 2, and that will give me 3a. Then that minus that's going to give me plus 3b, and that equals to 0. And I plug that in. And that tells me then that I can replace b with minus a. So let's hold that thought. I can replace b with minus a. Righto, so using the information so far, we've got this particular condition. So I can plug that back into, say, the first equation. So I get 4a. b I can replace with minus a, so that's minus 2a plus c, and that's got to be 0. And that tells me then that c is equal to minus 2a. So let's hang on to that one. So that means now, back in the original polynomial, I can replace both the b and the c purely in terms of a. So therefore my polynomial p looks like ax squared minus ax minus 2a. And I can factor out the a. And now I can think of this, now think back into linear algebra. This is the span of the polynomial x squared minus x minus 2. And that polynomial satisfies both of these conditions. It belongs to S, and I can build all of the polynomials in S from this one polynomial. So, conclusion, the polynomial x squared minus x minus 2 is a basis for this subspace S, and the dimension of S then will be 1, the number of basis vectors.